In today's video, we're gonna talk about magnetic fields of moving charges. Biot and Savard realized that when a current flows through a wire, it creates a magnetic field. And this magnetic field is given by the following equation, that it's the magnetic permittivity in free space, and the value of it is 4 pi times 10 to the minus 7 Teslas per meter over the current unit, that it's ampere. And we can see that from this equation we have the current that it's creating the magnetic field, that is current. We have the distance, the vector of the distance from where we're gonna measure our magnetic field, and the value of it, that would be the distance, the ratio, please, distance, and ds, that is the differential length vector that would tell us how much length does our wire has. So the differential vector. So the direction of the magnetic field is given by the right-hand rule. Well, one of many, that is. We have that our thumb would be pointing the direction of the differential, that our index would be pointing to the ratio vector. Oh, sorry, I did the unit vector. The vector. And that the component of the magnetic field would be given by the middle finger. This would be the right-hand rule for the magnetic field. Moving on with magnetic fields due to current distribution, we will start with a simple wire where we can find our diagram built like I'm gonna draw it. Sorry. We would have a current flowing through the wire, and we would know that the differential length vector would be always pointing at the same direction as the current. We would also know that this would be our unit vector for the ratio, or the distance. This would be the ratio vector of what we want to measure. This would be theta, because it is quite important, and this would be the perpendicular distance from what we are measuring our magnetic field. And least but not that it's not important, S, that is the distance from which we're gonna measure our magnetic field. So the equation that we can obtain from this diagram is that the magnetic field is equal to the electric permittivity times the current over 2 times pi times the perpendicular distance of what we want to measure. Another important thing in magnetic fields due to current distributions is when we have the interaction between two parallel wires. Two parallel wires have current flowing through them generate in magnetic force acting on them. So we're gonna analyze what is happening between the interaction of the wire number 1 and the number 2, but mostly what is happening in the wire number 2. So we would generally have that the force between these two, either one of them would be given by the general equation that would be the current times the length of our wire times the magnetic field that is acting on the wire that we want to know times sine of theta, that would be this one. And if we want to know focus more on what is happening in this wire that I've already told you that I marked properly. It would be the current too, since we know that this is interaction that we are taking like importance, the length of the wire, and the magnetic field of the wire number 1, since it is creating the force. So since the magnetic field of wire number 1 and the wire are perpendicular, we would have the force of 1 acting on 2 would be given by the equation that it's permittivity times current number 1 times current number 2 times the length of the wire times 2 pi the distance, that would be the one separating the two wires. And following Newton's third law, we would have that the force of 2 acting on 1 would be the same as the minus of the 1 acting on 2. That is the simplest analysis that we can take from Newton's third law. So moving on with Ampere's law, from what we have seen in electric field analysis, we know that Gauss' law helps us to make the analysis of electric fields more easy. So we know that Ampere's law helps us to make the analysis easier for the magnetic fields. So Ampere's law establishes that you can calculate the magnetic field in any area, but preferably that it would be cylindrical. And so it makes, imagine that we have this plane in which would have many currents going out of it, or maybe we would have one going out into it. This would be I2, I3, many of them. So what Ampere's law does is to establish an Amperian trajectory So we would make an analysis of what is happening inside of the Amperian trajectory. That would be given by the enclosed integral of the magnetic field times the differential length vector that we've already talked about, and that would be the electric permittivity times the current enclosed. So making an approach in the cylindrical analysis and using Ampere's law, we would know that the magnetic field would be given by the next equation, and we would have to take in consideration again the perpendicular distance that we've mentioned in the past whiteboards. Another important topic is atom magnets. Well, atoms acting as magnets. So we know that electrons are moving all of the time, or at least, So we can know that the current would be given as the magnitude of the electron times the period, not times, over the period of time that they are moving. So we can analyze this as if it could also be 2. So this would be velocity of our electron, and this would be the distance from what we want to measure. So taking all of this in consideration, that the electron generates loops because they are in movement, we can know the magnitude of the dipolar moment. So the magnitude of the, I'm not going use this anymore. The magnitude of the dipolar moment of an electron is given more by the velocity times the magnitude, well, the value of the electron times the distance over 2. And with this, we can also find the angular movement that would be given by, it would be the distance times the mass of the electron times the velocity, or 2 times the mass times the dipolar moment magnitude over the value of the electron. Since these two are vectorial, we can also find that the dipolar moment magnitude would be given by and from this we can also find the spin. That is something that we usually see in chemistry, and the spin cannot be defined because it is like mass. We cannot describe what it is, but we can say that the spin generates the electrons and other particles have their own angular moment. So the spin is given by the magnitude, that is a half of a constant that I just forgot, and it could be either plus or minus depending on how the spin is given. So with this we can have the magnetic moment that would be given by ms g, that is the numerical value of the electron, times the charge over 2 times the mass times s, that is the angular moment or the spin. Okay, now I'm gonna erase all of this and we're gonna talk about magnetic properties. So let's talk about magnetic properties of matter. We will find magnetization, that is given by letter M, and it establishes that magnetic dipole moment created by the dipole moments that are the atoms per unit volume, and we can use this for finding the magnetic field. This is the magnetization. We also have intensity, magnetic susceptibility. That is given by Cm, and we'd have intensity of the magnetic field that would be given by the letter H. With this one, we have 2 options. Either it is diamagnetism, which means that once the magnetic field is extracted from the thing that we're getting, the dipole moments will align with the current, and we will also have paramagnetism. And this is the magnetization lines up in the same direction as the magnetic field. We also have something very important that has to do with the magnetic susceptibility, that is ferromagnetism. That is a property that metals, so as cobalt, nickel, and others, have of having a magnetic field, but they are depending on the temperature, and we can have from Curie's law what would be this like limit of temperature. This would be Curie's constant. Now let's talk about magnetism and superconductivity. To close that, we would have a quick problem that we're gonna solve. Let's talk first about solenoids and toroids. So solenoids and toroids. Yeah. So a solenoid, there is an uniform intense magnetic field. We would have it here. We would have the current that it's going out of the plane, and this would be going inside of it. We'd have the magnetic field that it's going in this way, following the current, and using the Amperian trajectory that would give him by this one. We could find what is the magnetic field inside the solenoid. That would give him by B, where N is the number of length that our solenoid has. When our solenoid joins from, well, it flexes that both ends end in contact, so that we would have like a donut. That's when we have a toroid, and so it is a cylindrical, it has a cylindrical symmetry. We can find this, and well, using again the Amperian trajectory, we can find this as so now, this is how we would find the magnetic field in a toroid. So now let's solve an easy problem, and that will be all for the video. In the problem, we're given that a solenoid in a detector, in a magnets detector, has a magnetic field of 0.5 Teslas, and the current flowing through it is of 0.4 kiloamperes, and the length of our solenoid is of 8 meters. So using the equation for the magnetic field establishes that the magnetic permittivity of free space times the current times the number of lengths, from which we can know that this is equal to the number of turns that we have in our solenoid over the length. So solving for n, that is the one that we want to find, we have the field, magnetic field times the length over the constant times the current is equal, well, solving and substituting up all of our values, we will obtain that the number of turns that our solenoid has would be 8 times 10 to the 3 turns. And this would be all. Talking a little bit about magnetism and superconductivity, well, for example, in MRIs, we need to make our magnets superconductive. We use Meissner's effect to do so. So when we low down the temperature, our magnetic field reduces the maximum, so we make these magnets superconductive. This allows us to remain, well, to let the magnet float, and this is used so that our magnets, our electrons in our body align. So that's how they can take images of our full body. That would be it.